Space and time are two fundamental pillars of the cosmos. But could they possibly end someday? And would we still exist without them? Join us as we discuss the possible end of space and time. The concept of infinity distorts so many things in physics. On one hand, it makes sense, that is, if we explore it within the confines of the second law of thermodynamics. But at the same time, we know well enough that there are other established concepts that outrightly violate this law. For instance, in the case of stars, they survive because hydrogen fusion produces more energy than it consumes, and somehow we can relate this life where normalcy exists in contrast to the general disorder of the universe. However, each of these scenarios are isolated and can be considered a snapshot of reality at different times. Still speaking about stars, they're able to evolve to become a red giant because they possess enough helium which facilitates helium fusion and releases more energy. But this process does not hold true forever. Somewhere down the line, the star produces iron nuclei which consumes more energy than they release. In the end, the implosion and shockwave-induced explosion that is created makes half of the star explode into an expanding shell of hydrogen gas and other particles. In other words, the internal core of the star enters into a state where most of the remaining atoms become compressed so much that they form an intricate lattice which traps the bath of electrons related to the atoms. Admittedly, the matter involved in this process is very dense and non-fusing, which means heat can only be generated from the emission of legacy photons, or of legacy. As electrons escape from the lattice, the white dwarf begins to crystallize from within. As a result, a newborn white dwarf is hot, but it's basically radiating already generated heat. With time, there will be no fuel to regenerate the heat. The star begins to cool and switch from red to brown and eventually black. Naturally, the white dwarf is quite small and typically about the size of our Earth. However, it retains about 60% of the mass of the Sun. Due to this phenomenon, white dwarf stars are known to be very dense, meaning the more massive they become, the smaller they are. Our very star, the Sun, is already halfway into its life cycle, and in about 5 billion years from now, which is equivalent to 28 billion years after the Big Bang, it will become a white dwarf through the very process we described earlier. But how does this relate to the end of space and time? Well, as the Sun nears the end of its cycle, it would naturally become hot. In fact, scientists estimate that in some 1.5 billion years from now, the Sun's temperature would be so hot that it might cause the Earth's oceans to evaporate. However, there is a good chance that the human race may have become extinct by then. Admittedly, scientists expect our civilization to become extinct within the next 500 million years. By our standards, that's a lot of time, but based on the cosmic scale, it's only about 3% of the age of our universe. But things could have been a little different if the Sun had more mass. For instance, if the Sun had about 40% more mass, it would eventually become a blue carbon dwarf, more like a diamond in the sky. And if it were about 1.44 solar masses, it would become a neutron star, which has its own complexity as well. Another pivotal member to the exotic cosmic zoo is black holes. In simple terms, black holes are supernovas which can also be formed from accretion. In the past, the concept has been discussed and expanded by great scientists like Albert Einstein, Chandrasekhar, John Wheeler, and the late Stephen Hawking. Unlike what you might think, black holes don't have infinite gravitational attraction. Rather, they have a very high density within their event horizon, similar to dense quark stars. Critically, the event horizon is a cosmic prison that traps everything that crosses its path, including the particles. This is made possible because gravitational curvature at that point is such that light itself cannot escape. Expectedly, scientists are not too sure what the event horizon is. They know for certain that it isn't really the actual radius of a star. Instead, it is believed that the event horizon is directly proportional to the mass of the stellar object, meaning a neutron star could well be the minimal size of a black hole, which is about 2.3 times more than the mass of the Sun. However, with galactic black holes, which sometimes measure up to 1 million solar masses or more, the radius could be as big as 1 million times the diameter of the Sun. Indeed, some scientists believe that the event horizon should have significant energy to create a spherical wall of fire from the dissociation of matter. However, this claim is nothing more than a hypothesis, at least for now, because it is not backed by any concrete evidence. On the other side, there has been other theories proposed about black holes that could effectively expose the singularity, which is a point of theoretical infinite density that marks the center of the black hole, if they're charged and spinning at the same time. Also, there have been some propositions with quite enough evidence which suggests that there is a domain of quantum gravitational mathematics that we've not developed or discovered yet. However, this domain, which possibly exists at higher levels of relativity, was extensively covered in Einstein's general theory of relativity. Initially, some schools of thought suggested that it disproved some of Isaac Newton's options, but that wasn't the case. However, it has discovered that this mysterious theory was only valid within some domains. Thinking about it again, if Einstein was wrong, as initially suggested, it would mean that we're able to travel faster than light. But that's currently not possible due to the long-age conflict between the rules of the quantum world and the rules of relativity as defined by Albert Einstein. Despite exploring and experimenting for decades, scientists are yet to find a quantum theory of gravity. However, the recent experiments around the gravity of waves has given us some glimmer of hope that we could perhaps exceed the limitations of relativity and the quantum world. Critically, our knowledge of infinites and singularities is not founded on hard facts. We only know they exist based on theories and equations which are supposedly incomplete. Nonetheless, they also inform our understanding of the end of space and time. Time is an interesting element to measure, especially in relation to space. Fred Adams and Gregory Laughlin described it using a technique known as the cosmological decade in their book, 5 Ages of the Universe. This scale runs from -50 to 50, with each decade representing 10 to the nth power years. That means the -50th decade represents the first 1/1043rd of a second, and perhaps coincidentally, that is also the smallest unit of Planck time, which is based upon Heisenberg's uncertainty principle. Furthermore, it is also known as the shortest meaningful unit of time, and you wouldn't be wrong to think of it as the tick of the universal clock. Currently, our universe has existed for about 13.77 billion years since the Big Bang, which is equivalent to the 10th cosmological decade, otherwise known as the baryonic era. In our universe today, there is a mixture of baryonic mass, including protons, neutrons, electrons, and so forth, and tons of dark matter interacting weakly. Once this era ends, the degeneration phase is set to kick in between the 13th and 14th era. By then, the local group of galaxies would have merged together with vast amounts of space between them. Consequently, the expansion of the universe, which would still be accelerating, will make the universe look much different from what it is now. By the 30th cosmological decade, which is about some 10 billion years from now, the universe would appear to shrink because, ironically, the expansion process would cause what's left to disappear beyond an event horizon. But this is where things get complicated because we'd be stuck in between 2 event horizons. This means we'll be outside the event horizon around black holes. At the same time, another black hole is created by the ever-expanding universe. More interestingly, when the density of space becomes too low, the tick of the universal clock will ultimately stop, and the universe itself will accelerate to the point where the scale of the event horizon is approximately a few orders of magnitude of the Planck length, which would inevitably signify the end of space and time. But luckily, scientists predict that it would also trigger a new Big Bang, where another cycle of life will begin.